This lecture will talk about the same basic structures we discussed in the last lecture. However, now the period is so much smaller than the wavelength that there are no diffracted modes. We have only that zero order mode. And it turns out a lot of interesting and very useful things happen. First, we'll discuss the effective medium theory, and what you'll see, waves of different polarizations see essentially a grating that behaves differently, and so it has artificial birefringence, if you will. We will use that to design anti-reflection gratings, so we can actually put a grating on top of a structure and prevent reflections, and that's neat because we can make things that are monolithic without needing an additional material. Wave plates is huge. We can convert between different polarizations using wave plates. Chiral media is very neat, doing polarization and rotation. And then, of course, polarizers. So, and these will just be some samples of what subwavelength gratings can do for us. First, what do we mean by a subwavelength grating? Notice on this slide we have the wavelength drawn with the blue line, but notice the period of this grating. So imagine a wave traveling vertically and entering this grating. This grating is so incredibly subwavelength that it really doesn't perturb the wavefront, and we have essentially a uniform wave propagating through this. It does not diffract into any other modes. We get only that zero order mode. But that zero order mode has some interesting properties when it's inside that grating. And here it is, really in one summary slide. I'm showing the same grating on both the left and right halves, except notice the polarization. Here our polarization is perpendicular to the grating grooves, or parallel to the grating vector, if you will. And here the polarization is parallel to the grating grooves, or perpendicular to the grating vector. So we will call this the perpendicular polarization. We'll call this the parallel polarization. And it turns out these two polarizations see a very different grating. So since nothing is diffracting here, this tends to act like a single uniform slab of dielectric that we show down here. And it's some average of the low and high dielectric constants that we're showing. But it turns out the average that this perpendicular polarization sees is different than the average that this parallel polarization sees. They see two different things. And in fact, the polarization on the left here will be a lower effective dielectric constant than what this parallel polarization sees. And that is very useful. So there's lots of papers on effective medium theory. This is just a closed form equation. Given the two dielectric constants that make up the grating, what is the effective dielectric constant given a wave traveling vertically through that grating, if you will? Well, the parallel polarization is really just a weighted average, where F is the duty cycle of the grating. So we have this high region. The thinner that is, and the larger the low index region, the smaller the duty cycle. And so we can calculate this for the parallel and the perpendicular polarization. Notice for the parallel polarization, we're just taking a statistical average of the dielectric constant. Down here, we're taking an average of the dielectric constant, but we're taking the average of the reciprocal of the dielectric constant. So these are the simplest equations. I would call these first order approximations for effective medium theory. There are higher order approximations. I'm showing you one here, but definitely read the literature on this. There's lots of other approximations for this. But the ones in the upper left here will get you very close and certainly suffice for this class. And in my opinion, I think if you really need that extra degree of accuracy, you really should resort to a rigorous model and calculate those exactly, as opposed to going with higher order equations. That's just my opinion. Another thing that happens, and very often we think, okay, given a grating, there's some effective refractive index. And it turns out that's essentially true. However, remember, when a wave hits an interface, even if it completely reflects from that interface, it actually penetrates. And some of that power ends up on the other side of an interface. So if we're looking at a grating, the energy within that grating, some of that is sticking out into the surrounding materials. So we would expect that the thinner that grating, the more significant the materials on the outside are. And in fact, that actually happens. So for very, very thin gratings, very, very shallow gratings, the effective medium theory doesn't hold up very well. And what these plots are showing is that essentially as our gratings become shallow, the effective material properties that we're calculating for different gratings change very drastically for very, very shallow gratings. So the moral here is, if we have a very deep grating, the effective medium theory does a pretty good job. The shallower it is, not so much, and that's simply because it's so shallow that the power outside the grating that's interacting with the grating becomes more significant. So we say that gratings are birefringent, and here's a summary. What I'm showing is one little unit cell of the grating, so we see a tooth running this way, and the actual grating, the grating vector would be oriented the other way. And the blue arrows here is the electric field polarization. We're talking about a wave propagating downward. So notice the electric field is always parallel to interfaces. And we can call this the TE polarization, if you will. And the other mode, we have the electric field polarized perpendicular to the interfaces. It turns out it's this first case, this TE polarization, or if we were modeling this with our two-dimensional finite difference frequency domain, this would be the E mode. This has the higher effective dielectric constant than this case. And so, why is that? So let's pretend we are simulating this grating using something from last semester, finite difference frequency domain. And it's very, very sub-wavelength. Imagine the grating period being a billionth of a wavelength. When the grating period is that short, the wave propagating through the grating, the wavefront does not really get perturbed. It is a uniform amplitude wave. So if we're modeling something in the E mode, we see our distribution of dielectric that forms the grating, but the E mode will have a uniform amplitude. If we model this in the H mode will also have a uniform amplitude. So both the E mode and H modes for a grating will have uniform amplitudes. Now let's think where the power is. The power is essentially epsilon times E squared plus the permeability times H squared. Well, if we're modeling the E mode, we really only need this term, and if we're modeling the H mode, we only need the other term. Both the E mode and the H mode give us uniform amplitude waves. However, when we're calculating power, given the electric field, we scale that by the dielectric constant. So if we were to look at the power in the E mode, it looks like this, and it gets scaled in the region of the grating, and in fact the total power gets enhanced because of that. The H mode is scaled by the permeability. However, most materials don't have a magnetic response, so we're ignoring it here, and what we see is that we still just have a uniform H field. So we end up having less of the energy inside the dielectric for the H mode, whereas over here there is more energy inside the dielectric than the H mode. So if more of the power is inside the dielectric for the E mode, we would expect that to have the higher effective dielectric constant. And that's exactly what happens. Some final notes on subwavelength gratings. Remember, the period has to be very, very, very small, much less than the wavelength. Now, practically, what is that cutoff? Most people would say about 1/10 of a wavelength. I've been surprised, and I've seen some devices work up to about 1/4 of a wavelength. But beyond that, what happens is the spacing is so large that now the wave can interact with that grating, and we get diffraction and waves bouncing around, and it starts becoming resonant. A subwavelength grating, there's no waves bouncing around, nothing is resonating. We would call it non-resonant. And once we are subwavelength, less than 1/10 of a wavelength, let's say, the period can be anything. So normally what I do when I'm designing these things is I make the grading period absolutely as small as possible so that I can still manufacture it and it forms well. But there's no way you can make it too small. It'll still work just fine. If those grading grooves are a billionth of a wavelength, it will have the exact same properties as if they're a 20th of a wavelength. So no problems there. They're very broadband. They will work the same from DC up to their cutoff. And what the cutoff is when the wavelength starts approaching the period of the grading and it becomes non-subwavelength. So they're very, very broadband, and that's unlike diffraction gratings. And also these subwavelength gratings, in my experience, are very tolerant to structural deformations as long as those structural deformations are random in nature. They can tolerate those pretty well. Now let's think about how we will use this to etch some grooves into a structure to form an anti-reflection grating. So before we get into even how we realize different materials, here is the basic problem with an anti-reflection layer. We have material 1, and it has a refractive index, an impedance, a set of material properties. We want to get into some second material. We know that there's reflections at an interface. So we put in an intermediate layer that will help us minimize reflections at one wavelength. And so if we know the impedance on either side of the interface, then the impedance of the anti-reflection layer is just the square root of the product of the two impedances, and we make the length a quarter wavelength. Typically, materials don't have a magnetic response, and we can do this in terms of refractive index or even dielectric constant. But the refractive index of the anti-reflection layer is just the square root of the product of the refractive indices on either side of the interface. And again, we make the length a quarter wavelength. As long as we do this, at that wavelength, we will have zero reflection. Okay, so at the top here is another drawing of our anti-reflection layer. Let's say we're going from medium N1 with refractive index N1 to medium with refractive index N2. We will stick a layer that has some refractive index that we know is the square root of the product of the two refractive indices, N1 and N2, and a quarter wavelength. Well, what if we don't have this refractive index? In fact, what we can do is we can build it out of the material N2 and just etch or somehow form some grooves in it. And this will effectively lower the dielectric constant, lower the refractive index in that layer. And if we choose the duty cycle correctly using our effective medium theory, we can simulate or emulate the actual refractive index that we would need for a homogeneous material. So here's how this works. First, we would calculate the refractive index, the effective refractive index that we need to realize in the layer. Then we calculate the grading period. This can be anything as long as it's subwavelength. So I'm just saying less than lambda over 10 here. Now we have two different possible polarizations, and we can solve those effective medium equations for the duty cycle, because we'll know what the effective index is we want to achieve. We know the effective refractive index we're matching into and the effective refractive index we're going into, and so we can calculate the duty cycle for both of our polarizations, and they will be different. So in fact, we can't, using this, design an anti-reflection grating that has zero reflection for both polarizations, at least not for a ruled grating. Then once we have that, we again make the length lambda over 4. So really, we're just etching grooves to lower the dielectric constant or lower the refractive index in that anti-reflection region so that we form an anti-reflection layer. Now what's cool, this particular one on this page is designed completely with the refractive index N2. So whatever that material is, this is monolithic. We've just etched some grooves into it and minimized reflections. Whereas on the top part, we would need a second material, and there could potentially be some interface issues. There could be some residual stresses if it's temperature cycling or having shock and vibration. That separate second material could delaminate or detach or fracture in some way. Whereas if it's monolithic, it's much more robust. So this is a pretty neat way to do things. So here's an example. Let's say we have a wave going from air into a ceramic material. So air has a refractive index of 1. The ceramic material we're saying here has a refractive index at 3 at a frequency of 2.4 gigahertz. Design a grating that will minimize reflections at that frequency. So the first thing we need to do is calculate the refractive index that our grating has to match. So the product of the two refractive indices that we want to match, and we get 1.732. So our grating has to have an effective refractive index of 1.732. Given that we can do this, we can calculate the depth of the grating, or the thickness, and that has to be quarter wavelength. And so given our refractive index of 1.732, speed of light, our frequency, blah, 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 it ends up needing to be 1.8 centimeters tall, the grating. Next, we need to choose the grating period. We want it to be less than 1/10 of a wavelength. Here I made it 1/20 of a wavelength. So since we know the free space wavelength, we can calculate. That means the grating period needs to be 6.25 millimeters, and in fact, it could be that or smaller, or maybe even a touch bigger. So we chose the grating period, but this does not enter into any other calculations, at least for first order effective medium theory. These are the two duty cycles that we would need to realize an effective refractive index of 1.732, either for the E mode or the H mode, as we've described them last semester. So given the fact that there's two different equations, two different duty cycles, we see that we can't zero out reflection for both of them at the same time. Maybe we could choose a duty cycle of 0.5 and do a trade-off, but it turns out there's a better way if we want to match for both polarizations. So given this grating we just designed, for the E mode we calculated we need a 25% duty cycle. So that's what this grating looks like, and if we simulate reflection from this structure using finite difference frequency domain, here's the plot that we get. And we've minimized reflection at 2.4 gigahertz, just like we wanted. Likewise, we had a 75% duty cycle, so it's almost the inverse of this one, for the H mode, and if we simulate reflection, we see that we do get minimum reflection at 2.4 gigahertz. And you might notice those dips do not fall exactly on 2.4 gigahertz. That's because we based this simply on a first order effective medium model. In fact, we could refine these and adjust them a little bit and center reflection exactly. But you see the first order gets us extremely close. Okay, so how important is this subwavelength stuff? So let's say we do the exact same thing, however, we make the period a half of a wavelength. Well, we see we have certainly really messed things up. So this is because when we deviate away from being truly subwavelength, the equations we're using for the effective properties are no longer valid. So the refractive index of our anti-reflection layer is something else, and it's also potentially diffracting, and that can cause problems. So we're certainly not doing a very good job. We need to make these truly subwavelength for them to work according to how we want them to. Well, what if this isn't good enough? What if we want really, really broadband reflection? Well, it turns out about the best thing you can do is make cones, some kind of triangles. So wow, look at how broad this low reflectance is. So you'll notice if you ever walked into any kind of anechoic chamber, typically there's these cones on the sides of the walls, and they very much help to absorb waves. Well, suppose we want to have zero reflection for both polarizations. Well, we would use some kind of cross grading of cones. And that's really what you see in anechoic chambers. And so now we have zero reflection for both polarizations. Now we're changing topics. Wave plates. So we've just designed these subwavelength gratings, and we've discovered that they possess a different effective refractive index or different effective dielectric constant depending on the polarization. So let's ignore the fact right now that we have a subwavelength grating. Maybe it's just a material that is anisotropic. It doesn't matter for right now. So we have this chunk of material shown in gray, and we'll say that it has an ordinary and an extraordinary axis. And we'll make the extraordinary axis be a slightly higher refractive index. If we launch a wave that's polarized parallel to the ordinary axis, well, that's the refractive index this sees. And it comes out still polarized that same way. If we have a wave polarized in the direction of the extraordinary axis, that's the refractive index that this wave sees. So these two different polarizations see a different refractive index, and in fact will travel through that chunk of material at different speeds. And we can see that the wave is clearly compressed in the bottom block compared to the top one because it's a higher refractive index. The wave is traveling slower, so the wave is more compressed. Typically, when we use these types of devices, it's usually a crystal. In this lecture, we'll be realizing them with subwavelength gratings instead of crystals, but here it could be a crystal or a subwavelength grating. But typically what we do, we excite them with a linearly polarized wave, but it's polarized at a 45-degree angle between the ordinary and extraordinary axes. Now, why are we doing that? Because then we excite both of those polarizations equally, right? Because we can decompose this 45-degree linear polarization into a vertical and a horizontal polarization of equal amplitude. So we usually excite it at 45 degrees between the two axes, and that actually sends energy into both the ordinary and extraordinary axes. So those waves propagate through this crystal or subwavelength grating, and one of the waves is traveling at a different speed and in fact can become out of phase with the other one. They go in phase, but since they travel at different speeds, they come out potentially out of phase. So when that happens, our polarization can completely change. So for example, if we give a 180-degree phase shift of one polarization relative to the other, then the net polarization, what we're showing in green, has flopped over by 90 degrees. And it's now orthogonal to the polarization coming in. So we can use this type of birefringence actually to control polarization. So we have what's called a half wave plate. In a half wave plate, there is a 180-degree phase shift between the two orthogonal polarizations inside the crystal or inside that subwavelength grating. So if we excite along a 45-degree angle illustrated by this plane, kind of leaning forward, if you will, after propagating through this block, it comes out leaning the other way. And that's because one of the polarization does a 180-degree phase shift, and now we're oscillating along a different axis. This critical distance for a half wave is called L pi. Pi for 180-degree phase shift. And we can calculate what that length is. And it's really just a half wavelength scaled by the difference in the refractive indices. So if the difference between your ordinary and extraordinary refractive indices is not very much, this length will be very long. It will take a very long device in order to get that 180 degrees. So for a compact device, we want the index contrast, if you will, or the strength of the birefringence to be quite high. So half wave plates change the handedness of polarization. We go here from being polarized along one axis to another axis at 90 degrees with respect to that. We've changed the handedness. Instead of a half wave plate, if we go half that distance, we have what's called a quarter wave plate. With a quarter wave plate, we can go from linear to circular polarization or from circular to linear. Now, why is that? Well, now, inside this crystal, instead of imparting a 180-degree phase shift, or one of the polarizations, we impart a 90-degree phase shift. And we know if we have two linearly polarized waves that are 90 degrees out of phase but otherwise equal amplitude, that is a circularly polarized wave. So a quarter wave plate goes from linear to circular. Or if we start with circular, it goes to linear. So this is actually our first metamaterial this semester. A subwavelength grating is a uniaxial metamaterial. It possesses along two axes, for electric fields oscillating along two axes, the same dielectric constant, and along the third, a extraordinary dielectric constant or extraordinary refractive index. So in fact, these are uniaxial metamaterials. Now we have illustrations of how we're using gratings to serve as wave plates. The thickest, the half wave plates, we can construct using the Birefringence from a subwavelength grating. This way we can build it from things that are ordinary and not anisotropic. We have artificial anisotropy due to the grating. So half wave plates will change the handedness of polarization and also change the handedness of a circularly polarized wave. So it changes handedness really of any polarization. Quarter wave plates, we go from linear to circular or circular to linear. So that's pretty neat and very useful. So we can analyze these things with our models and get some rigorous solutions. I'm not going to spend a whole lot of time on this slide other than that there's two important conclusions here. The thicker the grating, the more stable our effective refractive indices. That made sense. Remember when we talked about thinner, shallower gratings, the fraction of power actually outside the grating becomes more significant. So the thicker the grating, the less significant that is, the more stable device we can design. Also, we want them very, very highly subwavelength. This is how we get the consistency in the effective refractive indices. Once we're below 1/10 of a wavelength or so, we can go all the way down to 1/1000th of a wavelength and we're seeing essentially the same effective properties. So we want to be as highly subwavelength as we can. As we start approaching the wavelength, different physics kick in. The lattices or the gratings start becoming a little bit more resonant, and the stability and the effective property we get aren't so much anymore. Here's one neat thing we can do with this. Imagine we have a linearly polarized wave. So we're talking about a wave that's propagating from top down, and the red lines I'm showing the polarization. So we have a linearly polarized wave. We showed that if there is a grating underneath a linearly polarized wave, that we can tilt that, we can rotate that. And in fact, by rotating the orientation of the grating, we can produce a linearly polarization on the other side, really in any orientation that we want to. So imagine we have a grating here over some surface, and we divide it into little sections. And we orient inside each one of these sections how the grating needs to be so that we produce a linearly polarized, a linear polarization on the other side in whatever orientation we want. We can actually create a beam that's radially polarized, or slightly different orientations here in the grating. We can create an azimuthally polarized wave. And what we'll see in a few slides, this is quite useful. But we are changing the orientation of the grating across the device aperture. So we can take a linearly polarized wave and create another beam with an arbitrary polarization distribution. Well, those have a problem. They have discontinuities between the square tiles, and that can produce another grating sort of superimposed on top, cause diffraction, scattering, and other problems. We prefer these to be smooth and continuous, and we get the form Birefringent devices. And so these are the equivalent gratings to what we had on the previous slide. However, these are smooth and continuous and work much better. We'll notice that the grating's compressed here, and it gets stretched as we move farther out. So at some point, either it'll be too tight here to manufacture or too spread out to be subwavelength. So there are some limitations here, but in principle, this is reorienting the grating however we would want to create a radially polarized beam. Or if we just turn the same thing 90 degrees, we get the azimuthally polarized beam. And these are called form Birefringent devices. So there's a very good reason for doing this. Some folks, and in the past we worked on this, where we were interested in exciting a metallic waveguide. And it turns out if the electric field is polarized perpendicular to a metal, boundary conditions say there can be an electric field inside that metal. We induce surface currents and there's a lot of loss. The boundary conditions for an electric field polarized parallel to the metal says that the field has to be zero at the metal. Well, if the field is zero at the metal, there's really not a whole lot of interaction there. We're not inducing currents, and in fact, that's a much lower loss beam. So it makes sense then, if we want to excite a metal waveguide with metal walls at optical frequencies, we would want an azimuthally polarized beam. And so, in fact, we did this. We made a form birefringent device. We shined linearly polarized light through it, and sure enough, out comes this donut-looking mode, and this really is the azimuthally polarized beam. On to chiral media. Everything in this course that we've taught, and in fact, even when I teach undergrad electromagnetics, I like to say there really is no such thing as a circularly polarized wave. There are only linearly polarized waves. When we have two orthogonally polarized linear waves that are 90 degrees out of phase and the same amplitude, we call that circular polarization, because if we track the electric field, it does circles. But I like to teach there's really only linearly polarized waves. Well, it turns out that model sort of breaks down in materials that are chiral and that also have what's called optical activity. And it turns out the most fundamental electromagnetic states inside these, because they're chiral and spiral in some way, are circularly polarized waves. And we can make materials that are birefringent to the circularly polarized waves. Now remember what happens when we combine two circularly polarized waves, we get a linearly polarized wave. And as we tweak the phase of those two circularly polarized waves, we still get linear, but it changes the orientation of the linear polarization. So if we have a crystal that's chiral and birefringent, meaning your right-hand circular wave and your left-hand circular wave see two different effective refractive indices, well, they may enter in phase, but as they propagate through the crystal, the right and left-hand circularly polarized waves become out of phase, and in fact, the overall effective linear polarization rotates. So we can think of exciting this with a linear polarization, and it rotates. And that rotation is called optical activity. So anything that is spiral in some sense is optically active and has the most fundamental electromagnetic states are circularly polarized waves. So there's some pictures of chiral type structures that produce this type of phenomenon. But even at the atomic scale, real crystals that do this, the atoms themselves are spiral in some way. And our last topic is polarizers. So here's a cartoon. If we have any polarization whatsoever, and it hits a polarizer, and here I'm showing a linear polarizer, we get only one pure polarization coming out. And in this case, it would be oriented vertically. So we hit it with any polarization, and it passes only one. That's a polarization filter, if you will, and we call that a polarizer. So now we want to learn about polarizers and how they work. We need a metric for how good a polarizer works, and what's used is what's called the extinction ratio. So imagine we have two polarizations that hit our polarization filter, and one of the polarization, a lot gets through. Some probably reflects, but the other polarization, a lot reflects and only a little bit gets through. If we look at the ratio of these powers, we call that the extinction ratio. So typical polarizers have extinction ratios maybe in the order of 100 to 1, but there's really, really high performance polarizers that have extinction ratios approaching 10,000 to 1. And there's probably ones even higher than that. So we will use the extinction ratio to essentially measure the performance of a polarizer. There's all different ways to make polarization filters. There's double refraction. Remember why we have double refraction? We have two different index ellipsoids, and the two different index ellipsoids correspond to the two different polarizations, an extraordinary and extraordinary wave. And so if we double refract, one polarization goes one way, the other polarization goes the other. And if we orient this correctly with the anisotropic crystal, we can separate the two polarizations. We also have the Brewster plates. And when we hit a wave at a Brewster's angle, we can get one polarization to reflect, other polarization to transmit, and separate our polarizations this way. Probably by far the most common is the wire grid polarizer, and we just have vertical continuous columns of metal or some kind of high conductivity material, and when a wave passes through that, it polarizes the wave. And there's also diffraction gratings. We've already learned there's a polarization effect in these things. The two different polarizations behave differently. We saw this when we were modeling. We had an E mode and an H mode, and they behave differently. So we can use this to separate polarizations also. Well, can we make a filter for circular polarization? Well, think of it this way. Instead of coming up with a filter for circular polarization, we can go back to our concept of wave plates. We can convert a circularly polarized wave to a linearly polarized wave. Then we can inject a polarization filter, and then if we need to, we can go back to circularly polarized. But we tend to filter circularly polarized waves by first converting to linear and then polarizing that. Folks make isolators with optically active materials and polarizers combined. So imagine we have some randomly polarized light or electromagnetic wave, and it passes through a polarizer. So it only passes a polarization that is up and down. Now it passes through a quarter wave plate, meaning we'll go from linear polarization to circular polarization, and it'll be a left-handed. It could be right-handed or left, but let's say it's left-handed. What matters is when it reflects, it changes handedness. And so in fact, then when it goes back through the quarter wave plate, what we have is our linear polarization now rotated 90 degrees, which will now be blocked by this linear polarizer. So this is called an isolator. It's like a one-way, it's like a diode for electromagnetic waves. They can go in, but they can't reflect back. And we can use this if we have a very sensitive transmitter, for example. It can transmit a wave, and we can be sure that nothing will come back to it. Wire grid polarizers. It turns out they actually transmit the polarization that is perpendicular to the metal wires. The polarization that's parallel to the metal wires does not pass. That gets blocked. Let's think about why that is. What's the difference between a metal and a dielectric? A metal has free charges. They're free to roam, and that makes things very, very different. Remember our discussion on Lorentz and Drude models. Well, our metals are running continuously lengthwise in this direction. So our electric field is polarized in that direction. It's pushing charges in this direction, and our metals are continuous. Those charges are free to move in that direction, and this acts very much like a continuous sheet of metal. However, if we have an electric field oscillating perpendicular to the metal wires, the charges are essentially stuck to the wire. And this acts very much, or much more like a dielectric than it does a metal. The charges are kind of bound. They're not free to travel across the surface. And in fact, this polarization is allowed to pass for that reason. This wire grid polarizer looks more like a dielectric than it does a metal to that polarization. So here's a finite difference frequency domain simulation of a wire grid polarizer. And the solid lines are the E mode, and the dashed lines are the H mode. And what we can see with the E mode is that we have reasonably high reflection. The H mode, the dashed lines, we have super high transmission. So there's actually a difference. We have very high transmission for the H mode and lower transmission for the E mode. And in fact, if we come over here to lower frequencies, we get very, very low transmission on the E mode and very high transmission on the H mode. So this is the most basic design. In fact, there's even better designs for wire grid polarizers, but that's basically how they work. And that concludes our discussion on subwavelength gratings.